Let's start today's sessions. First of all, I want to thank all of you joining us today. And originally, we were scheduled to hear a talk from Hiroki Takizawa titled "How I Solved the Game of Othello: A Deep Dive into Game Solving Techniques." But unfortunately, due to illness, he is unable to make it, and we apologize if you were looking forward to his presentation. And instead, we are thrilled to welcome Jonathan Schaeffer, who will be giving a talk on checkers, titled "Computer and Human Perfection at Checkers." A very huge thank to Jonathan for stepping in on such a short notice. And let me introduce Jonathan briefly. So he earned his bachelor's degree from the University of Toronto in 1979, and both his master's and PhD degrees from the University of Waterloo in 1980s and 1986, respectively. And currently, he is a professor in the Department of Computing Science at the University of Alberta. He also served as the president of the ICGA, the International Computer Game Association. His research focuses on artificial intelligence and computer games, particularly heuristic search techniques. Jonathan has been involved in some groundbreaking projects. He is the leading author of Chinook, the first checker program to win a world champion title in a competition against human players. He also contributed to Polaris, a poker program developed by the Computer Poker Research Group at the University of Alberta. And today, Jonathan will share his insight on proving that checker is a draw if both players play optimally. His groundbreaking work on this topic was published in Science in 2007. Okay, so please join me in welcoming Jonathan for this talk.
Thank you very much for the kind introduction. Like most of you, I'm actually disappointed to be here in this role. It was only a few hours ago that we got the unexpected and unfortunate news that we had to cancel today's keynote talk. So what I've done is mash together some slides. If people want to drop off and come back in an hour for the paper presentations, I'm certainly not going to feel offended. But this talk seems to be appropriate given that Othello has now been solved, and there's a lot of similarities between what Takizawa has done for Othello and the work that we did in checkers. So I'll call this a refresher course on solving games and a precursor to what Takizawa has done. And for those who are interested, his paper is online and you can download it and read it. So I'm going to talk about the game of checkers. It's popular in North America and the former British Commonwealth. In Europe, it's often called drafts. There are many variations on the game. The one that's most popular is on the 8x8 board. You really don't have to know much about the rules. You actually don't even need to know the rules for this talk. But the checkers that I'm talking about is the pieces move diagonally one square forward. Kings can move one square diagonally in any direction, and you can jump over pieces. And of course, when a piece goes to the last rank, it gets promoted to becoming a king. Computer checkers was one of the original grand challenge problems for AI. The first working program and the first publication goes back to 1953, and the early research is dominated by Arthur Samuel's seminal work. Samuel's amazing because his two papers on his checkers program really concentrated on the learning he wanted to put into his evaluation function, which was really a precursor to reinforcement learning. And so what's amazing is that his papers, even though they're from the 1950s and 1960s, are still heavily cited today. What's interesting is the first public man-machine competition was held in 1963. And a few years later, there was an exhibition match between Samuel's program and human world champion Predictably, back then, the computer lost decisively, 8-0, if I recall. Well, when I wanted to get involved with checkers, we had a very difficult problem because originally I wanted to build a superhuman program. And this was the obstacle. This is Dr. Marion Tinsley, who was really the best player in the world from 1950 to 1992. He was not world champion for those 42 years because in 1958, he basically got bored with the game because he was so much better than everybody else, and he retired. Um, he returned many years later and was just as good as ever and continued as world champion. But since this is an academic presentation, here's a quiz. The question is, in those 42-year period, how many games of checkers did Tinsley lose? And of course, I'm setting you up because if you answered 88, you're wrong. If you answered 51, you're wrong. And if you answered 37, you're wrong. The answer is 3 or 5. 3 is the official record. In those 3 games, those were tournament games. So there was a game in 1958 where he had a drawn position, made a one-move blunder, and lost. There was a game in the 1980s when the same thing happened. It was a drawn position, and he made a one-move blunder and lost. There's only one recorded game in these 42 years where Tinsley basically got outplayed. That's absolutely amazing. If you ever asked Tinsley how many games he lost, the answer was 5, because when Tinsley counted games, he counted every game that he ever played. And that means when he went to a shopping mall and would play 40 humans simultaneously, those counted as games. And over those 42 years and thousands of games that he played as exhibitions, he lost 2 other games. This man was more of a machine than a man because he was close to perfection as you could possibly imagine in a human. And this is the person that we want to beat. Well, in 1990, my program entered the human tournaments and earned the right to challenge for the World Checkers Championship. In 1992, Chinook played a match for the World Championship, the best of 40 games. Tinsley won 4-2. First of all, we won 2 games, which in itself is stunning. Second of all, the match was closer than it looks. We were actually leading 2-1 when, unfortunately, something bizarre happened and we had to forfeit a game, which made it 2-2. Tinsley legitimately won a game to go up 3-2. And then in the last game of the match, I set the program to go all out for a win. And as you can predictably imagine, that backfired and we lost. So it was a very close match. In 1994, Chinook came back, bigger, better, stronger, faster, and was playing incredibly well. But unfortunately, Tinsley became ill and had to withdraw. And that's how we won the championship. And we later defended the title, winning a match. Tinsley died in 1995. And after his passing, computers were, as Chinook demonstrated, were unquestionably far superior to humans. The problem is I had a credibility problem because I started getting hate mail. For example, one letter said Chinook doesn't hold a candle to Tinsley, and another said in his prime, Tinsley would crush Chinook because the humans, well, they loved Tinsley. He was such a great player. Of course, Tinsley got sick. You never have beaten him if he wasn't sick. Well, there was only one way that I could prove that the machine is better than man, that the computer program was or could be better than Tinsley. And if Tinsley was almost perfect, then the only way to dispel all these claims was to build a program that was perfect. And of course, solving games. This is a slide from 2007. Connect 4, Gomoku, Cubic, Nine Men's Morris, Awari, some hex board sizes, and subsequently a few more games, and in particular Othello. So solving games was nothing new, but checkers was daunting. Um, all these solved games have smaller search complexity and or simpler decision complexity than checkers. The search complexity can easily be quantified. It's 5 times 10 to the 20, and that's a lot of positions. And at the time, Awari was the biggest game that had been solved, so it was 10 to the 7 times bigger. So definitely an ambitious project. And the decision complexity with long games, multiple move choices, non-trivial decision making made it a hard game for computers and for humans. I want to emphasize the long games aspect to put it in context with Othello. Othello, every move fills in a square on the board. And since it's an 8x8 board, there's only 64 moves possible in the game. And since the first 4 square moves are already played, the 4 center squares in an Othello game, there's really only 60 moves. So a game must end in 60 moves or less. Whereas in checkers and in chess, because we're going to get a talk in the next the Wednesday, Thursday session on solving chess, the long games make these games much more difficult to solve because, at least in checkers, as you'll see, games can run hundreds of moves long, which makes the entire search much more daunting if you're trying to solve the game. I like this quote, which a professor told me. I had explained that I wanted to solve checkers, and it was 5 times 10 to the 20th, and he laughed. And I said, yeah, what I'm going to do is I'm going to solve checkers, and I'm going to write one fantastic paper and get it into the journal Science. And he said, what a moron. Don't you know how to play the publishing game? And what he implied is that's not how you do research. You have a problem like checkers and you find some small improvement and you publish a paper and then you improve it a little bit more and you publish another paper and a little bit more and another paper. You can get a whole career worth of papers publishing checkers. And I said, no, I really want one paper. I want to get my paper in Science. That's my goal. So apparently I am a moron for deciding that I wanted to go for gold and publish one paper in Science. The approach that used to solve the game was two-pronged, bottom up and top down. And bottom up is very familiar to people in this audience. Of course, retrograde analysis, building these large endgame databases, or today we might, many people call them table bases. And these are positions near the end of the game where we've computed the perfect information result, whether it's a win, a loss, or a draw, saved it in some sort of repository. And this allows us to reduce the search effort in that when a forward search reaches one of these positions, it doesn't have to do any searching. It can just look the position up in the database and get the perfect win-loss draw result. The second is top-down. Typically in a game, you can't build a database of all the positions in a game. So you've got to start at the top and search until you reach the databases. And as you'll see, there's 2 parts to it. It's a master-slave relationship where the master has this overall vision and this proof tree, and you have all these workers or slaves, and the master would assign pieces of work that the workers would then go and search and return the results to the master. And the master then would decide what additional nodes in the tree needed to be searched. So I'd like to talk about each of these components briefly. So here's what the solving process looks at the diagram. Now, first you'll notice that the scale, the vertical scale, goes from 0 to 24. That is the number of pieces on the board. And the width, the horizontal width, is the logarithm of the number of pieces. So, for example, here with only one piece on the board, you're talking about order, let's say 10 to the second number of positions. And here at 24, you're talking about order 10 to the 20th. You'll notice that there's a slight curve at the top here because actually with 23 pieces on the board, that's the maximum number of the maximums, the database with the biggest size. When you get to 24 pieces, it's slightly smaller. It's tapering off a bit. What you can see here in the graph is that, as I'll talk about shortly, with our in-game databases, we solved all positions up to 10 pieces on the board. So this entire portion of the search space, we have perfect information, win, loss, draw. Up here with 24 pieces on the board, 12 aside, is where the game starts. The solid line is the master. And what the master does is build a proof tree, and this solid line represents its current view, its current proof of what it's looking at to try and solve to determine the result of the game. And as it does that, it identifies positions that need to be searched, each represented by each one of these dots. And these individual dots represent positions that a worker would have been given, and it would try to solve it. And the worker might be able to solve that position or might not. Whatever it could do, it would return back to the master, and the master would be better informed and possibly change where it looks to try and solve the game. So here are the endgame databases. We used retrograde analysis to solve positions from this end of the game backward. We only stored the result, win, loss, or draw information. Unlike chess table bases, they store the win, loss, draw information, but they also store the distance to conversion. For solving the game, I didn't need to know the distance. That would have been nice, but it would have required considerably more storage. What you don't appreciate is that I started building these databases in 1989. In 1990, because the databases were getting big, I had to buy my first 1 gigabyte disk. Now, a gigabyte, that doesn't sound like a lot, but you have to recall in 1990, that was like groundbreaking commercial technology. At that time, I had to buy 2 of them. Each of them cost $5,000 plus tax. Obviously, the cost of a gigabyte has come down considerably since then. As you can see here, as the number of pieces are added to the board, the number of positions goes up. When we played Tinsley in 1992, we had all of the 7-piece databases and about half of the 8-piece databases. 2 years later, when we played him in 1994, we had all of the 8-piece databases in 1994. So that contributed to the strength of the program, but because I was trying to prove the game, we continued the computations and got up to all of 10, 39, million, billion, trillion, 40 trillion positions. Now, when you have that much storage, you need to manage it. And so we came up with some clever application-dependent algorithms to compress the data. So if you look at this, if this is a gigabyte, we would have needed like 40,000 gigabytes in order to solve this if it was 1 byte per position, but we only needed a result. And using real-time compression, we got it down to 250 gigabytes. And that works out to about 20 positions per bit, which is, for the time, was incredibly efficient. This was critical to us because, again, I'm talking about early day technology. Computers were very slow back then. And the smaller the databases, the more I could keep in memory. I never had a gigabyte memory way back when. So it was actually quite a lot of work to organize the data. particularly for spatial and temporal locality so that we could minimize expensive disk I/O. Even so, with clever organization and preloading of data and whatever, we could eliminate typically 99% of the I/O. But because of the way we were doing searching, we were searching quite deep and hitting the database quite often. The program was still I/O bound. 99% of the I/O gone sounds impressive, but it wasn't enough way back when. Here's an example of the endgame databases in action. If you do a quick count, you'll find there's 5 white pieces, 5 black pieces. This position is famous in the checkers literature because it's called the 100-year position. You don't need to know the subtleties of it. But if you can stretch your imagination back before the internet, in the year 1800, this position was posed as a problem. It's white to move. Is it a win for white or is it a draw? And everyone expected, well, the white king moves from here to here, and gosh, it looks like a win. And the original article said it's a win, and with lots of analysis. And a few years later, without the internet, of course, in the early 1800s, there was an article in a competing checkers magazine. They published an article saying, no, it's a draw. And a little while later, somebody published an article saying, no, it's a win, and back and forth. The position was posed in the year 1800, and by the year 1900, the checkers literature had come to the concluded that this is white to play and win. Well, checkers grandmaster Don Lafferty gave me this position one day and said, hey, you got your databases. This is a famous position. What's the result? And of course, it just took one database lookup, and the answer is a draw. And he was shocked. So he said, show me the analysis. And it turns out that the human analysis is flawed at move three of all, in that the computer creates an impenetrable fortress that is so unhuman-like. Humans had overlooked this defense for 100 years. So now the position is often referred to as the 197-year position, because it was posed in the year 1800 and we solved it in the year 1997. So these databases can be incredibly powerful. And keep in mind that the game of checkers starts with 24 pieces on the board. If 14 come off, you're into the databases. Here's another aspect of the endgame databases, which I really didn't publish much about. There is a paper on it, but I didn't give it much profile. This is work I did with Nathan Sturdivant. You'll notice that we have all of the 10-piece databases here. And at the time when I stopped computing the databases, to go to 11 would have been like another order of magnitude. And getting to 10 stretched all of the technology that I had. And the possibility of going to 11 pieces was just inconceivable at that time. But what we did is create what we call partial information databases. Having all the 10-piece databases, you could back up some of those results into the 11-piece database and actually compute some percentage of the 11-piece database based solely on the results that you've obtained from the 10-piece database. And although it wasn't a large fraction of the 11-piece and even some of the 12-piece databases, you could do that computation. And impressive as it was, we didn't actually use it in the solving process because it added much more data to our proof program, and it increased the I/O dramatically. In some positions, it reduced the search effort by 10%. Sometimes it reduced the search effort by 90%. That's amazing. That's fantastic. But again, I/O was the limiting factor. Costly disk I/Os just killed us. All right, let's talk about the master process. So we've been building from the bottom backward. And now we want to go from the start of the game with 24 pieces and find a proof where all of the leaf nodes are in the database. The database is perfect information, so I need to find a path from the start of the game into the databases. So the master process maintains the proof tree. So the leaf nodes in the proof tree are win, loss, draw, which we get right out of the database. But sometimes we have partial results in that we have a node that we know we've been able to prove is not a win, but it could be a loss or a draw, or a position that we've proven is not a loss, but it might be a draw or a win. And so there are proven nodes and partially proven nodes. The master would build the tree using the best first search proof numbers algorithm, which most of you are well known or familiar with. So it would build this proof tree. And once it traversed the tree, it would generate a whole bunch of positions who, if we could solve them, would help inform the tree and allow us to make progress towards proving the game. A lot of the work was quite useful, but some of it turned out to be useless because if you have, say, 100 computers working, traversing the proof tree might generate only one node and say, hey, this is the one best node you should evaluate. Well, that's great. And I can send it to a worker, but what's the point of only sending one piece of work when you have 100 machines, because 99 of them are going to sit idle. So we would generate work for the nodes that we knew we had to expand, plus a whole bunch of other ones that we thought were high probability that we might have to expand in the future. And so we would give that, generate enough work for the workers to try and keep them busy. And the workers would return the results, the proof tree would be updated, the master would then traverse the proof tree and generate more work, trying to make further progress. As a result of generating a lot of work to keep the workers busy, you'll find that it varied, but about 25 to 30% of the work that was actually done by the workers turned out to be useful for the proof tree, and about, say, 70 to 75% of the work that was generated turned out to be irrelevant. You know, if you generate 100 pieces of work and one piece of work comes back and says, hey, I found the solution at a node, well, then the other 99, their work was wasted. But we deliberately generated lots of work to keep the machines busy. The workers would look to a queue and take the first piece of work on the top of the queue, go off and search it, and then return it, let the master know that the work was done, and the master would then update the proof tree. The workers actually did two searches. The first was a fast search, and it was a heuristic search. It used alpha beta. It was basically Chinook with some modifications. Each of these searches typically, say, would take less than 10 seconds, but could take a minute or so, depending upon how complex the position was. These were typically set to be 17-ply searches with search extensions. Some moves might be cut off early for heuristic reasons. There's the possibility that they would search deep enough into the database and return a win or a loss result. But even if it didn't, it would return a useful value, which was the heuristic assessment. So the positions that Chinook thought were very favorable would get a positive score, an unfavorable, a negative score, and something that was drawish might be plus or minus 0. Having done the heuristic search, we would then, if the position wasn't solved, we would then do a slower search, a proof number search, to see if this position could possibly be proven. And we would do that depending upon the result of the heuristic search, if it looked possible that we might be able to prove it. And sometimes we get the win-loss draw perfectly, sometimes we get the bound, and sometimes we would get no useful result. So the heuristic search was always done, and sometimes the proof search was done, and there was no guarantee that either of them would actually find a proof, but at least we would get some heuristic information which would help guide the master as to which moves were reasonable moves to continue exploring and which were unreasonable. The master did an unusual form of iterative deepening on its proof tree. It would iterate on the error in the heuristic search. So the master would start with would be given a threshold H. And this could be heuristically set to a value, or it could start just above 0 and keep iterating. But the idea of H was that if the value that was ever returned by Chinook for a position was greater than H, then we would call it a likely win. It's not a proven win. Of course, if it was proven win, then we don't need H. But if it returned a heuristic score and the value was greater than H, then we'd say, it's probably a win. May not be, but okay, probably. If it was below negative H, then hey, it's probably a loss. Might not be, but heuristically. And then given this, it allowed us to search and build a tree which contained proven wins, proven losses, possibly likely wins, possibly likely losses. So if you look at the range of all values, if we've got a plus infinity, that was a proven win. If we had a negative infinity, that was a proven loss. But if a search returned a value greater than H, it was likely a win up here, and negative H below it, a likely loss. And otherwise, we'd get this heuristic value in here. Higher in values may not be likely wins, but perhaps they're suggestive. Negative values bigger than negative H, perhaps suggesting we're in trouble, and possibly around draws. And what we would do is the master would search this and get a heuristic result. And typically, of course, when you start with your first H, you don't prove the game, but you prove whether the value is greater than H or less than negative H or between. And if it's between, you keep going until you get above H or minus H. And so, for example, if you assume that H was one checker, we're going to start off and say, hey, H is one checker, which means that if we ever returned a value greater than one checker, then we're going to say it's a win. If the value came back less than -1, less than one checker, we'd say it's probably a loss. And we would go through and we would come up with a search tree, and we now have a result. We would then increase H to 1.1, a little bit bigger H. And now we would go through the proof tree again. And many of the branches, they don't change at all. In other words, using H equals 1 gives us an outline of what the proof tree probably looks like. Doesn't mean it's right, but it's with high probability pretty close to the proof. We then increase H to 1.1, and now a lot of things stay the same, and a few things get corrected. And we keep repeating it until H becomes big enough that there's no more error, if you will, in the search. So what we found is that values beyond 1.0, so if we ever returned a value, heuristic value greater than 1, it was more than 99% accurate that it was a win. There were a few exceptions. If it was less than -1, it's probably a loss, very few exceptions. And we never saw an error for any value greater than 1.75. So the heuristic method gave us a good proof outline, and subsequent refinements to it improved it. And at some point, like around before we reached 1.75, there was no error in the search. But we, of course, had to keep doing the search until we were able to turn nodes from heuristic values into proven values. So here are some of the results. Now, checkers, you can start off with 12 pieces aside, but in checkers tournaments, because the standard position is well known to be a draw, they have what's called a three-move ballot, which means at the beginning of a tournament game, you have a deck of cards and you choose from the deck of cards, and the card tells you the first three moves of the opening. So here, with black moving first, you might have seen the three-move opening as moving. Black must move his checker from here to here. White moves his checker from here to here. Black moves his checker from here to here. And now the game starts. And what you do is, because some of these positions are still pretty balanced and some of them are quite unbalanced, you play a pair of games against the opponent. You play one game against the opponent with black, and when it's over, you play the second game with colors reversed. And so we chose this opening as our the one that we wanted to tackle as our first step. And this opening, some of the checkers openings have names, most don't. This one is called the White Doctor. And this is one of the most challenging openings for humans to play because it's a very dangerous opening for black. And this is an opening that has a long history in the game and has a very personal history in the Chinook versus Tinsley battles. And so this was the first opening that we were able to use our techniques with the masters and worker processes to be able to try and solve. And in January 2005, we were able to do that and prove a draw in this one line. It was a good learning experience and allowed us to refine our algorithms to make them better. The White Doctor took many, many months of computing using less than 10 machines. And part of the problem was that the searches were limited by I/O speed, which of course forced us to do whatever we could to get machines with more memory or bigger caches, as well as reorganizing the data to try and compress it so that it was smaller, to try and reorganize the data to have better spatial and temporal locality. One of the things that, I always knew, but it's only when you see it happen that it becomes so frustrating. In this opening, you could blatantly see that the opponent always takes the line of maximum resistance. It's trying to avoid the proof. And so, for example, in a position which it's obviously drawn, then the program could take one line and go into it and say, hey, if I play this line, I get into the 10-piece database where I've got 5 pieces, my opponent's got 5 pieces. I can look it up in the database and hey, it's a draw. Great. But of course, the program, if you were going to prove that this position is a draw, okay, this one position leads to a draw. That's great, but the program will look at all alternatives because it'll try to avoid the draw. It's still trying to win. And so it will play ridiculous moves, sacrifice pieces, and might, for example, go into a position with 8 pieces versus 3, which of course is terrible and is losing, but it's unknown. It's not proven. It's not a proven win. It's not a proven loss because it's not in the database. And so you would see these lines as the program tried to avoid, let's say, the inevitable. Very frustrating. Just made for more work. If you want to solve the game, you need to solve more than just this White Doctor opening. There's 400 possible 3-move openings. I want to solve the position at the start of the game, 12 pieces aside, not just the White Doctor. When you take a look at the 400 3-move opening sequences, there's just under 200 if you eliminate all the transpositions. So there's 200 3-move openings that we potentially would have to solve, but of course, we're going to use alpha beta to make that even smaller. So if you look at a 3-ply search tree, this is the minimal alpha beta search. You got a bunch of moves at the root, and this is your principal variation. And along the principal variation, you need to solve all of the children, and then you have this and/or effect where some nodes are ands and some nodes are ors. And if you just do the quick math using this, you see that there are n lines here that need to be explored. If our branching factor is n along this line here, these three positions or n positions need to be solved. Here, on all the children of this branch, there's only one if you have a perfect minimal tree. And so there's n minus 1 times just one node here. And over here, you've got, we've taken care of this branch, but we have n minus 1 branches left to consider. And each of them might have n children that need to be solved. And if you do the math there, you get n squared plus n minus 1 moves. If at the beginning of the game your branching factor is 7, then that would mean you would need to solve not 200 three-move openings, but only 55 three-move openings. So 55 opening lines, if you could solve them and they came back with the value that you think you're expecting, then maybe you've solved the game. But you can do even better. One thing about checkers is that capture moves are forced. And so if you look at this line here where black plays a move and white plays a move, and now it's black's move, what I did is tackle openings, choose the opening sequences of moves to minimize the size of the search tree. So if black makes this move, I'd say, let's explore the opening where white plays this move, a particular move, and black is now forced to capture here, which means instead of n moves, if there's only one capture, there's only one move that is played, which means instead of n moves there, I only have to consider one. And here there's n minus 1 of these, each of one as being 1. And on these other lines here, if black plays this move and white plays this move, we choose white's move in such a way that black again has to capture. And we get a n minus 1 of these lines, each with only one move, which works out to 2n minus 1, which means in theory, there's only 13 of these three-move openings that need to be solved. And if all 13 turned out to be a draw, then this tree would be minimal and the draws would back up and the root would be proven as a draw. And in fact, this is what happened. Once we'd computed the databases, the 10-piece databases, I then had 50 processors working in parallel on the proof. So we solved the White Doctor, which was our prototype in January 2005. We reworked the data, we reworked the algorithms, and then for 2 years, we had 50 computers running virtually nonstop with the master and the slaves working. The longest line in the proof tree was 154 moves. Remember, I'm going to compare that back to Othello, where in Othello, the longest line is 60 moves. And so again, it's hard to compare Othello to checkers because of the long lines that you see in checkers and chess. They make the search much, much more difficult. So the longest line in the proof tree is 154 moves. But remember, at the end of that was a search, a Chinook search. It was a minimum of 17 ply. And because of search extensions, many of those positions had lines that were well in excess of 30 moves. And eventually, that search would have returned a proof value, which could be in the database. And I don't know how long the longest winning or the longest resistance losing position in the database is, but I do know it's more than 250 moves, which means in theory, if you didn't have the databases, you might have had to search over 400 moves and possibly considerably more than 400 moves deep, in this case, a move being 1 ply, in order to be able to prove some of the lines. And so that really is quite daunting. but doing smart things like paring down the search tree at the root, building the databases, trying to build the proof tree in the master using heuristics so that we get the minimal proof tree or as close to the minimal proof tree as quickly as possible before doing all the expensive searches to actually turn the heuristics into proven values. We only had to search about 10 to the 14th positions, which still is a big number, but you have to remember checkers is 10 to the 20th. So we basically, were able to reduce the search by 6 orders of magnitude, which is what, a million, a factor of a million. An important thing in the search is correctness. There were several things that needed to happen. The graph history interaction was a very important problem, and I was delighted when Akihiro Kishimoto and Martin Mueller solved that problem and published in AAAI 04. And of course, they were at the University of Alberta, and we had Kishi help implement the GHI solution in the checker solving program. Bugs are my nemesis. I'm sure that's true for all of you as well. I had to deal with disk I/O failures, more common than you think. Network failures. In a proof, everything's got to be correct, and that meant that everything had to be checked and double checked. For example, when we did copying of files over a network, you would think, hey, I copy a file over a network. Sure, it's going to be copied correctly. Yeah, and it does most of the time. But every so often, with the amount of data that we were moving around, 15, 17 years ago, a file would copy and it would be the right size, but the contents might be slightly wrong. And that's kind of scary. We all assume computers are 100% reliable. Memory parity errors, that can happen. I had a disk file which was verified to be correct, absolutely verified to be correct. 2 years later, we found an independent verification of the databases found an error in it. And we traced it back. We found that 1 bit of over multiple gigabytes was wrong, but the original file from 2 years before had been correct. So somehow in those 2 years, 1 bit got flipped, and all the computations that had relied on that database in those 2 years, I had to throw out because I could not verify when that error occurred, and I had to assume that everything was incorrect. So there were lots of things that we had to do. In the end, every computation was verified, and as many people will know, oftentimes a verification process is more expensive than the computation process, and it did suck up an enormous amount of time. And I was very fortunate, at least through the 8-piece databases, that we had independent verification so that we knew that our code was working correctly. Fellow in Britain had re-implemented everything on his own, and eventually we were able to get both of us the identical results. So that was all very important. And this is my career ta-da moment. So if neither side makes a mistake, then the game of checkers will end in a draw. So I now have a theorem. Anybody who knows me, I build systems. I don't prove theorems, but I do have a theorem now. Perfect play leads to a draw. And my proof, I have a construction. And interesting, most people don't know when they prove something, but I do. I know that on April the 29th, 2007 at 5:01 p.m. California time, while I was in a hotel in California, my program stopped running. I thought it was a bug until I looked at the log files, and there was the words, ta-da. I put that in a shell script many, many years before. And got surprised when it suddenly appeared there on my screen. Ta-da! So there's a corollary here that if perfect play leads to a draw, then since Chinook has got the proof, Chinook will never lose. And the implication, going back to the beginning of the talk, Marion Tinsley was almost perfect, but occasionally he made a mistake. Therefore, I conclude that my program is better than Tinsley. My program will never lose. And we may have to play lots of games against Tinsley, but he would have eventually made a mistake. It was wonderful, the recognition that we got for solving checkers. The journals Science and Nature ranked it as one of their top 10 breakthroughs for 2007. New York Times called it the death of checkers, and they had this wonderful picture here of a human being buried beneath presumably 10 to the 20th checkers positions. And DARPA initiated solving games of national importance. But most importantly for me, I got what I wanted. I got my paper in science. And I wrote a book about it. The first book came out in 1997 about Chinook when we won the Human World Championship. It's a very personal book. It's high level, non-technical, and full of stories and anecdotes. It's something I'm very proud of. And then when we solved the game, I took the book and revised it and extended it to bring the story up to date. And to be quite honest, I'm the paper in science and these books are the accomplishments in my academic career that I am most proud of. And so this wouldn't have happened without the efforts of a lot of people at the University of Alberta. Perhaps a few of these people are actually on the call today. And so I want to thank all of them. They turned my dream, which was started in 1989, into reality in 2007, 18 years later. Something about obsessive compulsive behavior seems to be appropriate. So with that, I'll stop sharing and say thank you, and I'm open to answering questions.
Okay, a big props to Jonathan's wonderful talk. And if you have any question, please feel free to use the raise hand function or use the QA or even chat. Okay, so far I have not seen any questions. Then probably I start from a very general question. So from your experience in solving checkers and also considering modern technologies like GPU or deep learning algorithms, what do you think is the most challenging part for solving bigger games like 10 by 10 checkers or chess or something like, in terms of like domain-specific heuristics or search algorithms, storage, or even computing powers?
So I guess Yap is going to give a talk in a couple of days on solving chess, but I'm actually pessimistic about solving chess, and it's not because it can't be done. Clearly it can be done. It just may not be able to be done in our lifetime. When you take a look at the methods or how we understand the games right now, you need storage, you need computing, and you need the algorithms. And chess is 10 to the 45th. And although you could say, well, boy, we can solve Othello, which is 10 to the 28th. Well, we can extrapolate into the future, and maybe in a couple decades we'll be able to solve chess. But I don't see it that way, because the databases are important, but we're not going to get, with current technology, disks that are 1 million or 1 billion times bigger. If you give me more computing power, give me 1 billion times more computing power, and I'm not going to solve chess. It's hard to see major improvements in the algorithms. We have alpha beta, we have proof number search, we have Monte Carlo search. I think we understand them pretty well. I don't see them giving me, 1 million-fold improvement. Better evaluation functions will help, because they will help guide me to the minimal proof tree. But if Chinook is off the minimal proof tree by a small constant, and the Othello proof is off the minimal proof tree by a small constant, you're not going to get much better than that. So I'm not sure how much more AI can help. I see it more as we need either multiple technological breakthroughs, of which quantum computing might be one, or we need a breakthrough in understanding the game. It might be possible that we learn some property that we can prove in chess, and if this property holds, the game with perfect play must be a draw. In other words, a little bit of knowledge might be able to eliminate a whole bunch of things that would be computationally hard to prove. So I'm a little bit pessimistic about the likelihood of solving harder games. And again, I pointed it out before, and I'm not trying in any way to be negative about the Othello result, but when you have no limit on the length of the game, those proof trees can be go enormously deep, and that will definitely be a challenge for solving games like chess, where if checkers requires hundreds applied in order to be able to solve some lines of play, I fully expect chess to be even harder because it's a much more complicated game. I see there's some questions in the chat, so maybe I'll
Yes. I will try to read out them.
comments.
First is from Yap. Congratulations.
Okay. Sure. So Yaron Shoham asks, nice to see that you're here, Yaron. What would you do differently today given the advances in search, AI evaluations, and hardware? There's a couple of things I would do. Of course, I use Chinook's evaluation function. I tried using neural nets with it in early 2000s and was able to build a tuned evaluation function that was comparable to Chinook's, but not better. I suspect with modern techniques, I could get an even better evaluation function, and that would allow me to build the proof tree in a more efficient way. So I can see a constant improvement in the proof by having a smaller proof tree. The hardware, of course, with today, I probably would have built the complete 11-piece databases, which would have reduced the search. I don't know that I could have done 12 today, but maybe. Then, of course, more memory means with the bigger databases, more caching. So the search would have gone faster, and I might have been able to significantly reduce the I/O, even though I was using bigger databases. So obviously technology would make a difference. What was hard doing this proof in the 1990s and early 2000s might actually be much, much easier today, given the hardware. The one thing that I did not address then, and is an open question, is how you would use GPUs in this kind of environment. That obviously could make, add order of magnitude or 2 orders of magnitude or more in terms of efficiency of the computation. So yes. Dave Gomback, you mentioned the 8-piece database was replicated. Has any further replication of larger databases or the solving proof occurred? To be honest, the answer is I don't know, because I'm not really into checkers. I don't play the game. And when checkers was solved, I basically moved on, and I haven't really followed any of the checkers literature. So it's possible they've been replicated. Certainly, I know of at least 2 groups in the mid-2000s that had independently built the 8-piece database. So it's quite possible. Yeah, points out the little bit of knowledge will help in the 8 versus 3 checkers. Yes, but as I discovered once when I tried to solve some of the lopsided positions, like in the 10-piece database, it says I have 9 pieces versus 1, 8 pieces versus 2. okay, 8 pieces versus two, it's pretty obvious who's going to win, but there are some pathological positions where the two pieces win. And so a little knowledge will help, but you still need to be careful and you got to make sure that it's absolutely correct. And I kept finding little cases in these lopsided positions because I thought, oh, I'm going to actually use a knowledge-based approach on these positions. And then I gave up and said, I'll just compute the whole bloody thing. Okay. Did you tell something on Tinsley's reaction? Um, well, first of all, he died, of course, before checkers was solved. Um, we played Tinsley twice for the World Championship, and that is a huge reflection of the quality of the man. He was the best player, the best human checker player ever, without a doubt. And he once said, not exactly in these words, but he said, one of the reasons he resigned the World Championship is because it was uninteresting to him. He was so much better than humans, and humans started playing boring checkers against him. They would always try to draw because you could never beat the great Tinsley. And so he found the games just boring and uninteresting. And then a computer comes along which has no human preconceptions and plays what humans might think is ridiculous moves, but are basically sound. And he said checkers was fun again. That's an actual quote. He said checkers is fun again because the computer challenged him. So that's why he wanted to play these world championships. He wanted to be challenged. So I think that having solved the game, knowing Tinsley and what a gentleman he was, he would have been the first person to congratulate me, and he would have also enthusiastically embraced looking at the data so that he could learn some of the secrets of the game of checkers. Bin Zawas says, perhaps your method could also be solved through quantum technology. Possibly. My knowledge, I won't claim to be an expert in quantum technology, but from what I know, I just don't see how we could use quantum technology effectively to solve games like Othello, like chess, like checkers. But of course, it's early days for quantum technology, and not just on the technology side, but also on the algorithm side. So if we want to solve chess, I think that's one of the promising ways that it could be done is through quantum technology, and as a challenge to our community to come up with search algorithms that are quantum friendly. Is it expensive to replay all solutions for verifications? We only have one solution. We found a proof. So we have one solution to the game, and I'm sure actually there's alternate equivalent ones in the proof tree, but all we needed is one. And that has been replayed and verified, the minimal proof tree, but I have not gone through the proof tree to find other solutions and verified that those solutions would be correct as well. And another question, what was the most rewarding feeling in all the years? This will sound silly, but keeping all these computers running was a full-time job almost. There were periods of time where literally I had dozens of monitors active on my terminal, monitoring all the computations, because certainly in the 90s and early 2000s, the mean time to failure was high. And I was monitoring everything, monitoring for errors, crashes, things like that, because whenever things crashed, to repair things and undo things was actually quite time consuming. And I wanted to make sure corrupt data did not get into the system. So, because I would have to, backtrack and restore previous versions of the data. So the most rewarding feeling after all that was the sense of relief that I don't have to do that work anymore. Of course, that's kind of silly with hindsight. Of course, the most rewarding feeling was the satisfaction that after 18 years, I stuck with the project through to completion, and that original vision of producing that one paper in Science was realized.
Okay, so I think it's almost the time to close this session, and I do see another question or comment from Ting in the chat, so maybe you can reply it later.
Which?
In the chat.
Sorry, I was in the Q&A. I didn't go to the chat. Sorry.
Okay, maybe
Sorry,
you can
do I have it?
reply later.
I'm not seeing another question under. Not sure which question you're referring to. I don't see another one. But if somebody has questions, you can just email me, jonathan@ualberta.ca. I'd be delighted to answer questions offline. So
Okay.
thank you very much. And I appreciate that you all stuck around for, I guess, an old talk. And like you, I am disappointed that we didn't have the keynote. And hopefully we'll be able to have him give a talk sometime in the near future.
Okay, thank you again for Jonathan's talk.
Right. Sorry, I just see the question now. It's in the webinar chat. I was looking under the chat. Sorry. Let me just answer it. What are the chances of getting published in Science or Nature now if a new game is solved? Well, poker. Michael Bowling published in Science in 2015. He solved two-player poker. There were also papers in Science and Nature about, I guess, superhuman multiplayer poker and superhuman Go, for example. So, Othello was published in Archive. I don't know if the Othello paper got published in a higher quality venue than that. I don't know about solving small board Go would have the effect. When I solved the White Doctor, the first opening, I wrote a paper and submitted to Science, and they said, nope, can't do it. Come back when you've solved the entire game. And so I think you'd get the same answer for Go. Solve the small board Go, that's great. Come back when you've solved the whole game. Okay, thank you very much, everyone. And we have some paper presentations in 15 minutes, so please stick around for them. It's an excellent set of papers today.
Okay, thank you, Jonathan, for the talk again.